Welcome to Quick MCAT Lessons, where I try to explain MCAT topics in 10 minutes or less. Today we're starting a new unit on enzymes. So enzymes are biological catalysts that speed up chemical reactions in living organisms without being consumed or permanently altered in the process. They work by lowering the activation energy required for a reaction to proceed, and this increases the rate at which equilibrium is reached. Now, despite this, enzymes do not change the overall free energy or the delta G of a reaction, nor do they shift the equilibrium point. They simply help the system get there faster. Think of having to walk to the other side of a tall hill. Walking all the way over is a way that would take a while, but if there's a tunnel going straight through, then it would be much easier to walk to the other side. Enzymes simply make it easier for substrates to reach their transition state. Now, enzymes are highly specific to their substrates, meaning each enzyme typically acts on one or a few specific molecules due to the shape and chemical properties of its active site. And the active site is the region where substrate binding and catalysis occurs. Now, for example, chymotrypsin only cleaves peptide bonds around phenylalanine, tryptophan, and tyrosine. And although these aren't the same molecule, they contain an aromatic ring, making chymotrypsin specific for a class of molecules. Now let's go over some key features of enzymes, starting with the fact that they lower the activation energy and they increase the rate of reaction. But they don't alter the equilibrium constant and they don't affect the thermodynamics of the reaction. They are pH and temperature sensitive and they are not changed or consumed in the reaction, which means they appear in both reactants and products. Now some basic terminology. So first we have the substrate. This is the molecule that an enzyme acts upon. Then we have the product. This is the result of the enzymatic reaction. The active site, which is a specific region of the enzyme where the substrate binds and the reaction is catalyzed. There's an enzyme-substrate complex, which is the intermediate formed when an enzyme binds its substrate. Now let's go over enzyme components. So starting with the apoenzyme. This is the protein portion of an enzyme. It's inactive on its own, as enzymes without their cofactors are called apoenzymes. There's also a holoenzyme, which is the active enzyme that includes the apoenzyme and its necessary cofactors or coenzymes. And so many enzymes require non-protein molecules called cofactors or coenzymes to be effective. These cofactors and coenzymes are small in size, so they can bind to active sites of enzymes and participate in catalysis of the reaction, usually by carrying charge through ionization, protonation, or deprotonation. They are usually kept at low concentrations in cells and are recruited when needed. So a cofactor is a non-protein, often inorganic ion, like magnesium or zinc, which is required for activity and is often ingested as a dietary mineral. A coenzyme is a small organic group, the majority of which are vitamin or vitamin-derived. So vitamin-derived would be like NAD+, FAD, or coenzyme A. The water-soluble vitamins include the B-complex vitamins and ascorbic acid, which is vitamin C. These are important coenzymes and must be replenished regularly because they're easily excreted as they're water-soluble. The fat-soluble vitamins A, D, E, and K are harder to excrete. It's also good to note that enzymes are not restricted to a single cofactor or coenzyme. For example, some metabolic reactions require magnesium, biotin, which is B7, and NAD+, which is derived from vitamin B3, simultaneously. Now let's talk about a prosthetic group. A prosthetic group is a tightly bound cofactor or coenzyme that is permanently associated with the enzyme. Before we finish off, I just want to clarify one quick thing. So we talked about how enzymes lower the activation energy. And so if you ever look at a graph of the delta G of free energy of activation energy, you'll see that there's a top of the activation energy. There's like a curve. So the very top point of that curve is the transition state. So enzymes essentially stabilize the transition state, and that's how they lower the activation energy. So enzymes are often more specific for the transition state than they are for the substrate. And this specificity is due to the active site's precise arrangement of amino acids, which forms an optimal environment to stabilize the transition state through various interactions. So activation energy is the minimum energy needed to initiate a chemical reaction, while the transition state represents a high-energy, unstable configuration through which reactants must pass to form products. Activation energy is denoted as EA, and it's the difference in energy between the reactants and the highest energy state. And the magnitude of this activation energy determines the reaction rate. Higher activation energies result in slower reactions. The transition state cannot be isolated or directly observed due to its extremely short lifetime. It's characterized by partial bonds where bonds within the reactants are in the process of breaking and new bonds are forming to yield product. With that, that's all for today. Next time we'll talk about enzyme classifications.